In this multiple-choice question, the command that automatically generates an IP6 address from a specified IP6 prefix and the MAC address of an interface is B. IP6 address 2001:D.B. 8to5:112:/64 UE64. Let's explain it further. UE64 is a method used in IP6 to generate a unique interface identifier based on the MAC address of the interface. It allows for the automatic creation of an IP6 address by combining a given prefix with an interface's MAC address, which is transformed into a 64-bit identifier. Option A, IP6 address DHCP, refers to obtaining an address via DHCP-v6, which does not involve generating an address from a MAC address. Option C, IP6 address autoconfig, is related to the stateless address autoconfiguration (SLAAC) method but does not specifically mention generating an address from a MAC address. Option D, IP6 address 2001:D.B. 8to5:112:264 link local, is a static assignment and does not involve the automatic generation of an address from the MAC. Referencing the CCNA 200-301 topic. The topic related to this command is most likely found under the section IP6 Addressing and Basic Connectivity Configuration Guide within the IP Addressing and Subnetting for New Users or Understanding IP6 Link Local Address. These sections cover IP6 address types and methods of address assignment, including UE64 addressing. Thanks for listening. Please don't forget to subscribe to my channel. See you in the next short lecture.
In this multiple-choice question, when configuring IPv6 on an interface, the two IPv6 multicast groups that are joined are D. FF0201, E. FF022. Let's explain further. FF0201 is the all nodes multicast address, meaning that all IPv6-enabled devices on the local link will receive packets sent to this address. Whenever an IPv6 device joins a network, it automatically joins this multicast group. FF022 is the all routers multicast address, which all IPv6 routers on the local link will join. This allows routers to communicate with each other without needing to send messages to every individual router. Option A, 2000:3, is a range for global unicast addresses and is not a multicast group. Option B, 2002:5, is an example of a specific IPv6 address and does not represent a multicast group. Option C, FC00:7, is a range for unique local addresses, ULA, and is not a multicast address. This topic would likely fall under IPv6 addressing and address types, specifically in sections covering IPv6 multicast addresses and IPv6 addressing and basic connectivity configuration. These sections discuss the types of IPv6 addresses, including multicast addresses and their functions in networking.
In this multiple-choice question, understanding network routes and IP routing. When a router needs to send packets to a specific host, it checks its routing table to determine the best path. In the case of the IP address 10.10.13.10, which falls within the network 10.10.13.025, the router, R1, does not have a specific entry for that host. Instead, it relies on a network route to reach the address. What are the key concepts? Network route. This is a route that directs traffic to a network rather than a specific host. In this scenario, R1 uses the network route for 10.10.13.025 to reach any host within that subnet, including 10.10.13.10. This means that R1 can forward packets to the entire subnet without needing a specific entry for each host. Routing table. The routing table contains various types of routes, including host routes, specific routes for individual IP addresses, e.g., October 10, 2013. 10:30 seconds. Network routes, routes that cover a range of addresses, e.g., 10.10.13.025. Default routes, a catch-all route used when no specific route is found. OSPF, open shortest path first, if the routing table indicates that the network route for 10.10.13.025 is learned via OSPF, indicated by an O in the routing table, It means that R1 is dynamically learning about this route from other routers in the OSPF area. Interactive analysis. Why use network routes? Network routes simplify routing by allowing a single entry to cover multiple hosts. This is particularly useful in larger networks where managing individual host routes would be cumbersome. How does R1 determine the route? When R1 receives a packet destined for 10.10.13.10, it checks its routing table. Since it finds the network route for 10.10.13.025, it forwards the packet accordingly. What happens if a specific host route exists? If R1 had a specific host route for 10.10.13.10, it would use that route instead of the network route. Host routes take precedence over network routes when both are available. In summary, R1 uses a network route to reach the host 10.10.13.10 because it does not have a specific entry for that host. This approach is efficient and aligns with the principles of IP routing and subnetting, allowing routers to manage traffic effectively across networks. This topic is part of the IP routing and subnetting section in the CCNA 200-301 curriculum, which covers how routing tables are constructed, the types of routes, and the principles of dynamic routing protocols like OSPF. Understanding these concepts is crucial for effective network design and troubleshooting.
In this multiple-choice question, based on the provided exhibit from Router 1's routing table, we need to determine which prefix Router 1 uses for traffic to host A, 10.10.13.214. Looking at the routing table. The relevant entries for the destination network, 10.10.13.0/24, include 0010.10.13.0/24, 10, via 10.10.10.1, 4 seconds, Gigabit Ethernet 0 is 0. 0010.10.13.144/28, 10, via 10.10.10.1, 4 seconds, Gigabit Ethernet 0 is 0. 0010.10.13.208/29, 10, via 10.10.10.1, 4 seconds, Gigabit Ethernet 0 is 0. To reach host A, 10.10.13.214, Router 1 would use the most specific route available, which is C. 10.10.13.144/28. This subnet includes the host IP address 10.10.13.214. This question relates to the topic of IP routing and addressing, specifically focusing on route selection and subnetting. In this multiple-choice question, based on the provided exhibit from Router 1's routing table, we need to determine which prefix Router 1 uses for traffic to host A, 10.10.13.214. Looking at the routing table. The relevant entries for the destination network, 10.10.13.0/24, include 0010.10.13.0/24, 10, via 10.10.10.1, 4 seconds, Gigabit Ethernet 0 is 0. 0010.10.13.144/28, 10, via 10.10.10.1, 4 seconds, Gigabit Ethernet 0 is 0. 0010.10.13.208/29, 10, via 10.10.10.1, 4 seconds, Gigabit Ethernet 0 is 0. To reach host A, 10.10.13.214, Router 1 would use the most specific route available, which is C. 10.10.13.144/28. This subnet includes the host IP address 10.10.13.214. This question relates to the topic of IP routing and addressing, specifically focusing on route selection and subnetting.
In this multiple-choice question, when a frame enters a switch and fails the frame check sequence, FCS, the two interface counters that are incremented are A. Input errors. D. CRC. Let's explain further. Input errors. This counter is incremented for any errors detected on incoming frames, including those that fail the FCS check. An FCS error indicates that the frame has been corrupted during transmission, which results in it being counted as an input error. CRC, cyclic redundancy check. This counter specifically tracks frames that have failed the CRC check, which is the mechanism used to ensure data integrity. A failed FCS is essentially a failed CRC check, so this counter will also be incremented. Option B, frame, is not a specific error type. It generally counts the total number of frames received and is not specifically related to error conditions. Option C, giants, refers to frames that exceed the maximum allowed size, usually 1518 bytes for Ethernet frames, and is not directly related to FCS. Option E, runts, refers to frames that are smaller than the minimum allowed size, 64 bytes, which is also not directly related to FCS failures. This topic is related to network access and understanding Ethernet frame errors within the CCNA 200-301 curriculum. It covers how switches handle frames, the types of errors that can occur during frame transmission, and how to interpret interface statistics to troubleshoot network issues. Understanding these concepts is essential for diagnosing and resolving connectivity problems in a network environment. In this multiple-choice question, drag and drop matches. 172.28.228.14418. Usable host range, 172.28.228.1 to 172.28.229.254. 172.28.228.14421. Usable host range, 172.28.224.1 to 172.28.231.254. 172.28.228.14423. Usable host range, 172.28.228.1 to 172.28.229.254. 172.28.228.14425. Usable host range, 172.28.228.129 to 172.28.228.150. 172.28.228.14429. Usable host range, 172.28.192.1 to 172.28.255.254. Explanation. /18, subnet mask of 255.255.192.0, creating a larger range of addresses. /21, subnet mask of 255.255.248.0, which allows for a smaller range. /23, subnet mask of 255.255.254.0, giving a usable range within the larger block. /25, subnet mask of 255.255.255.128, resulting in a smaller range of usable addresses. /29, subnet mask of 255.255.255.248, creating a very small range. Note: make sure to verify the ranges based on the subnetting rules and calculate usable IPs accordingly, considering that the first address is the network address and the last is the broadcast address in each range. Understanding IP4 subnetting and usable host ranges is a critical skill in networking, particularly in the context of the CCNA 200-301 exam. The specified topics provide foundational knowledge and practical skills needed to calculate and identify usable addresses within given subnets, which is essential for effective network design and management.
In this multiple choice question, the correct answer to the question about how TCP and UDP differ in the way they establish a connection between two endpoints is A. TCP uses the three-way handshake, and UDP does not guarantee message delivery. Explanation. TCP, Transmission Control Protocol, is a connection-oriented protocol. It establishes a connection between two endpoints using a process known as the three-way handshake. This involves SYN, the client sends a SYN, synchronize, packet to the server to initiate the connection. SYN-ACK, the server responds with a SYN-ACK, synchronize acknowledge, packet, indicating it is ready to establish the connection. ACK, the client sends an ACK, acknowledge, packet back to the server, completing the handshake and establishing a connection. UDP, User Datagram Protocol, on the other hand, is a connectionless protocol. It does not establish a connection before sending data and does not guarantee message delivery, order, or integrity. This makes UDP faster but less reliable compared to TCP. Analysis of other options. B. TCP uses synchronization packets, and UDP uses acknowledgement packets. This statement is misleading because TCP uses synchronization packets, SYN, for establishing connections, but UDP does not use acknowledgement packets at all. C. UDP provides reliable message transfer, and TCP is a connectionless protocol. This is incorrect. TCP provides reliable message transfer, while UDP is connectionless. D. UDP uses SYN, SYN-ACK, and FIN bits in the frame header, while TCP uses SYN, SYN-ACK, and ACK bits. This is incorrect. TCP uses those bits for connection establishment and termination, while UDP does not use any of these bits. This topic is found under TCP/IP Overview and What is the Difference between TCP and UDP in the CCNA 200-301 curriculum. These sections cover the fundamentals of TCP and UDP protocols, their characteristics, and how they function in data communication. Understanding these differences is crucial for networking professionals as they impact how applications transmit data across networks.
In this multiple-choice question, the correct answer to the question about which 802.11 frame type is association response is A. Management. Let's explain it further. Management frames. In the 802.11 wireless networking standard, management frames are used to establish and maintain connections between wireless devices. The association response frame is a specific type of management frame sent by an access point, AP, to a client device in response to an association request frame. This process is part of the initial connection setup for a wireless client to join a network. Other frame types. Protected frame. This is related to security features and encryption within frames but is not specifically about the association process. Action frame. Used for specific actions like requesting to change a channel or power management. These are also part of management but not specifically the association. Control frame. Used for acknowledging the receipt of data frames and providing feedback regarding the status of communications. They do not handle association. This topic is associated with wireless fundamentals and specifically under wireless LANs and 802.11 frame types in the CCNA 200-301 curriculum. The wireless fundamentals section discusses the principles of wireless networking, including the different types of frames used in IEEE 802.11 networks. It covers how wireless devices communicate, the role of management frames in establishing and maintaining network connections, and the different types of frames, such as management, control, and data frames. Understanding these concepts is essential for configuring and troubleshooting wireless networks effectively. This knowledge helps network professionals manage wireless LANs and ensure reliable communication in various environments. In this multiple-choice question, the correct answer to the question about how a spine and leaf architecture allows for scalability when additional access ports are required is C. A leaf switch can be added with connections to every spine switch. Let's explain it further. In a spine and leaf architecture, the leaf switches connect directly to the spine switches. Each leaf switch typically connects to every spine switch in the network. This design enables horizontal scalability, allowing for additional leaf switches to be added without disrupting existing connections. When more access ports are needed, you can add more leaf switches, and since each leaf switch has connections to all spine switches, this helps balance traffic loads and maintain low latency. Other options. A spine switch and a leaf switch can be added with redundant connections between them. While redundant connections are important for reliability, simply adding a spine and leaf switch does not specifically address scalability in terms of adding access ports. B. A spine switch can be added with at least 40 GB uplinks. Adding a spine switch with high-capacity uplinks is beneficial, but it does not directly relate to the scalability of adding access ports. D. A leaf switch can be added with a single connection to a core spine switch. This option does not utilize the full potential of the architecture since it only connects to one spine switch, which could create a bottleneck and reduce redundancy. This topic is included in Network Fundamentals and Data Center Networking sections of the CCNA 200-301 curriculum. The spine and leaf architecture is a network topology commonly used in data centers to provide a scalable and efficient method for connecting servers and storage. The architecture consists of two layers. Spine layer, composed of high-capacity switches that handle the traffic between leaf switches. Leaf layer, composed of switches that connect to the servers and endpoints. This design allows for multiple paths between devices, ensuring low latency and high throughput while maintaining balance in traffic distribution. It simplifies the scaling process, enabling network administrators to add more leaf switches as needed without significant reconfiguration of existing infrastructure. Understanding this architecture is crucial for modern networking, especially in environments requiring high performance and reliability.
In this multiple-choice question, the correct answer to the question about what identifies the functionality of virtual machines is C. The hypervisor virtualizes physical components including CPU, memory, and storage. Let's explain it further. A hypervisor is a software layer that allows multiple virtual machines, VMs, to run on a single physical host. It virtualizes the physical components of the host system, such as the CPU, memory, storage, and networking. This enables each VM to operate as if it has its own dedicated hardware, allowing for efficient resource utilization and isolation between VMs. A. The hypervisor communicates on Layer 3 without the need for additional resources. This is misleading. While hypervisors manage networking, their primary function is not about Layer 3 communication specifically. B. Each hypervisor supports a single virtual machine and a single software switch. This is incorrect. Hypervisors can support multiple VMs and multiple switches. D. Virtualized servers run efficiently when physically connected to a switch that is separate from the hypervisor. This statement does not accurately describe the core functionality of hypervisors or virtual machines. This topic is relevant to a network fundamentals and a network function virtualization found in the CCNA 200-301 curriculum. Network function virtualization, NFV, refers to the process of decoupling network functions from hardware appliances and running them as software applications on virtual machines. This approach allows for greater flexibility, scalability, and resource efficiency in managing network services. The hypervisor plays a crucial role in this architecture by enabling multiple virtual machines to share physical resources while providing isolation and management capabilities. Understanding NFV is critical for modern networking, as it aligns with trends toward more agile and programmable network environments. It supports the deployment of various network services, such as firewalls, load balancers, and routers, in a virtualized manner, enhancing the overall efficiency and adaptability of network infrastructures. In this multiple-choice question, the correct answer to the question about the default behavior of a Layer 2 switch when a frame with an unknown destination MAC address is received is C. The layer 2 switch floods packets to all ports except the receiving port in the given VLAN. Let's explain it further. When a layer 2 switch receives a frame with an unknown destination MAC address, meaning the address is not in its MAC address table, it does not know where to send the frame. To handle this situation, the switch floods the frame to all ports in the same VLAN, except the port on which the frame was received. This ensures that the frame reaches its intended destination if the unknown MAC address is connected to any of the other ports in the VLAN. Other options. A. The layer 2 switch forwards the packet and adds the destination MAC address to its MAC address table. This is incorrect because the switch cannot forward the packet if it does not know the destination MAC address. B. The layer 2 switch sends a copy of a packet to the CPU for destination MAC address learning. This is also incorrect. Switches do not send packets to the CPU for learning purposes. D. The layer 2 switch drops the received frame. This is not the default action. Dropping a frame occurs in specific conditions, such as when security policies dictate it. This topic is part of the Network Access section within the CCNA 200-301 curriculum. The Network Access section covers the fundamental concepts and operations of Layer 2 switching in Ethernet networks. It includes discussions on how switches learn and store MAC addresses, the operation of VLANs, and how frames are processed and forwarded based on MAC address tables. Understanding the behavior of switches when encountering unknown MAC addresses is crucial for network design and troubleshooting, as it influences how traffic is handled and affects overall network performance and efficiency. This knowledge is essential for configuring and managing switches in various networking environments.
In this multiple-choice question, to configure a /30 subnet between two routers, we need to identify the usable IP address and subnet mask combination that meets this requirement. A /30 subnet provides 4 IP addresses in total, with 2 usable addresses, which is suitable for point-to-point links between routers. The valid options and analysis are as follows. A. Interface E0/0 description to 20AXXX. XXXXX IP address 10.2.1.325.255.255.252. Subnet 10.2.1.030. Usable IPs 10.2.1.1 and 10.2.1.2. Valid configuration. B. Interface E0/0 description to 20AXXX. XXXXX IP address 192.168.1.1.255.255.255.248. Subnet 192.168.1.029. Usable IPs 192.168.1.1 to 192.168.1.6, 6 usable addresses. Not a /30 subnet. C. Interface E0/0 description to 20AXXX. XXXXX IP address 172.16.1.4255.255.255.248. Subnet 172.16.1.029. Usable IPs 172.16.1.1 to 172.16.1.6, 6 usable addresses. Not a /30 subnet. D. Interface E0/0 description to 20AXXX. XXXXX IP address 209.165.201.225.255.255.252. Subnet, the mask provided, 225.255.255.252, is incorrect, should be 255.255.255.252. If corrected to /30, would be valid if it were a proper configuration, but as written, it is invalid. The best option that meets the criteria for a /30 subnet is A. Interface E0/0 description to 20AXXX. XXXXX IP address 10.2.1.3255.255.255.252. This question relates to the topic of IP addressing and subnetting found in the CCNA 200-301 curriculum. The IP addressing and subnetting section covers the principles of IP addressing, including how subnetting works and the implications for network design. It includes discussions on how to calculate usable IP ranges, the significance of subnet masks, and the methods for creating subnets that efficiently utilize IP address space. Understanding subnetting is critical for configuring networks and ensuring efficient communication between devices, especially in scenarios like point-to-point links between routers, where using the correct subnet size is essential for optimal performance and resource utilization.
In this multiple-choice question, to determine which network allows devices to communicate without the need to access the Internet, we need to identify which of the given options represents a private IP address range. Private IP addresses are used for internal networks and do not require access to the global Internet. Analyzing the given options. A172.9.0.0/16. This IP address is part of the public IP address range since it does not fall within the private IP address ranges defined by RFC 1918. B172.28.0.0/16. This address is part of the private IP address range. The 172.16.0.0 to 172.31.255.255 range is designated for private use. C192.0.0.0/8. This address is part of the public IP address range. The 192.0.0.0/8 range is not a private range. D209.165.201.0/24. This address is also part of the public IP address range. To conclude, the only option that allows devices to communicate without the need to access the Internet is B172.28.0.0/16. This topic falls under IP addressing, particularly a private versus public IP addressing in the CCNA 200-301 curriculum. A few words about the IP addressing section. It covers the fundamentals of IP addressing, including the concept of public and private IP addresses. Private IP addresses are defined in RFC 1918 and can be used within private networks without the need for Internet connectivity. The designated ranges for private IP addresses are Class A, 10.0.0.0 to 10.255.255.255. Class B, 172.16.0.0 to 172.31.255.255. Class C, 192.168.0.0 to 192.168.255.255. Understanding these concepts is essential for network design and configuration, as they dictate how devices communicate within local networks versus needing to access external resources. This knowledge is crucial for ensuring proper network segmentation, security, and efficient use of IP address space in various networking scenarios.
In this multiple-choice question, the correct answer to the question regarding which IPv6 address type provides communication between subnets and cannot route on the Internet is B. Unique local. Let's explain further. Unique local addresses, ULA's IPv6 unique local addresses are designed for local communications within a site or between a limited set of sites. They are not routable on the Internet, meaning they are meant for private network use only, similar to IPv4 private address ranges, like 10.x/x, 172.16.x/x to 172.31.x/x, and 192.168.x/x. ULAs typically start with the prefix FC00:7. At link local, these addresses, starting with FE80:10, are used for communication within a single network segment and cannot be routed beyond that segment. However, they are not meant for inter-subnet communication. C. Multicast. This is a method to send a packet to multiple destinations at once, but multicast addresses can be routed on a network and are not specifically for private, non-internet use. D. A global unicast. These addresses are routable on the internet and are intended for public communication. This topic relates to IPv6 addressing in basic connectivity in the CCNA 200-301 curriculum. A few words about the IPv6 addressing in basic connectivity section. This section covers the structure and types of IPv6 addresses, including global unicast addresses, unique local addresses, link local addresses, and multicast addresses. This topic emphasizes how different address types serve various purposes within network architecture. Understanding these address types is crucial for configuring networks that utilize IPv6, ensuring efficient routing, and implementing security measures in both local and wide area network environments. The knowledge of IPv6 addressing is essential for modern networking, especially as organizations transition from IPv4 to IPv6 due to address exhaustion and the growing demand for IP-enabled devices. In this multiple-choice question, the correct answer to the question regarding which IPv6 address type provides communication between subnets and cannot route on the internet is B. Unique local. Let's explain further. Unique local addresses, ULA's IPv6 unique local addresses are designed for local communications within a site or between a limited set of sites. They are not routable on the internet, meaning they are meant for private network use only, similar to IPv4 private address ranges, like 10.x/x, 172.16.x/x to 172.31.x/x, and 192.168.x/x. ULAs typically start with the prefix FC00:7. At link local, these addresses, starting with FE80:10, are used for communication within a single network segment and cannot be routed beyond that segment. However, they are not meant for inter-subnet communication. C. Multicast. This is a method to send a packet to multiple destinations at once, but multicast addresses can be routed on a network and are not specifically for private, non-internet use. D. A global unicast. These addresses are routable on the internet and are intended for public communication. This topic relates to IPv6 addressing in basic connectivity in the CCNA 200-301 curriculum. A few words about the IPv6 addressing in basic connectivity section. This section covers the structure and types of IPv6 addresses, including global unicast addresses, unique local addresses, link local addresses, and multicast addresses. This topic emphasizes how different address types serve various purposes within network architecture. Understanding these address types is crucial for configuring networks that utilize IPv6, ensuring efficient routing, and implementing security measures in both local and wide area network environments. The knowledge of IPv6 addressing is essential for modern networking, especially as organizations transition from IPv4 to IPv6 due to address exhaustion and the growing demand for IP-enabled devices.
In this multiple-choice question, the two reasons that cause late collisions to increment on an Ethernet interface are B. When one side of the connection is configured for half duplex. E. When the cable length limits are exceeded. Let's explain further. Half duplex configuration. When one side of a connection is set to half duplex mode, it can send or receive data but not both simultaneously. This can lead to increased collisions, especially if both devices attempt to transmit at the same time, resulting in late collisions as they interfere with the ongoing transmission. Exceeding cable length limits. Ethernet has specific maximum cable length limits, e.g., 100 meters for fast Ethernet over twisted pair cables. When these limits are exceeded, signal degradation can occur, causing packets to be corrupted or lost. As a result, late collisions can increase because the devices may not be able to detect collisions properly due to poor signal quality, leading to retransmissions. Analysis of other options. A. When carrier sense multiple accessor collision detection is used. This is a standard method used in Ethernet to manage collisions and does not inherently cause late collisions. Rather, it helps prevent collisions. C. When the sending device waits 15 seconds before sending the frame again. This behavior does not directly cause late collisions. Waiting for a random back-off time is a part of the collision avoidance mechanism. D. When a collision occurs after the 30-second byte of a frame has been transmitted, this is a definition of a late collision. But the question asks for reasons that cause late collisions to increment, not the definition itself. This topic relates to Ethernet and collision domains, which is part of the Network Access section of the CCNA 200-301 curriculum. The Ethernet and collision domains section covers the fundamentals of Ethernet networking, including the concepts of collision detection and avoidance in half-duplex and full-duplex environments. It explains how Ethernet operates over various media types, the importance of adhering to cable length specifications, and the implications of using half-duplex connections. Additionally, it discusses how collisions can impact network performance, particularly in shared media environments, and the significance of understanding collision domains in network design and troubleshooting. This knowledge is crucial for ensuring efficient network communication and minimizing issues related to collisions in Ethernet networks.
Hello all. The correct answer to the question about the benefit of using a Cisco wireless LAN controller is A. It eliminates the need to configure each access point individually. A Cisco wireless LAN controller, WLC, allows for centralized management of multiple access points, APs, within a wireless network. This means that the configuration changes, software updates, and monitoring can be handled from a single point rather than configuring each AP separately. This centralization simplifies network management, reduces the likelihood of configuration errors, and enhances scalability as new access points can be added with minimal effort. Relevance to CCNA 200-301. In the CCNA 200-301 curriculum, one of the key topics covered is wireless fundamentals, which includes understanding the architecture and management of wireless networks. The role of wireless LAN controllers is an important aspect of this topic, as they facilitate efficient wireless network operation, especially in larger environments where numerous access points are deployed. Understanding how to manage wireless networks using controllers is essential for network engineers, making this knowledge critical for CCNA certification. A Cisco wireless LAN controller centralizes the management of wireless access points, allowing network administrators to configure and monitor multiple APs from a single interface. This capability streamlines operations, reduces administrative overhead, and minimizes configuration errors, making it a vital component for effective wireless network management, especially in larger deployments.
Hello all. The correct answer to the question regarding the action taken by a switch port enabled for PoE, Power over Ethernet, Power Classification Override is D. If a switch determines that a device is using less than the minimum configured power, it assumes the device has failed and disconnects it. Analysis and relevance to CCNA 200-301. Explanation of action. In a PoE-enabled switch port configured with Power Classification Override, the switch monitors the power consumption of connected devices. If it detects that a power device, PD, is drawing less power than the configured minimum threshold, it interprets this as a failure condition. Consequently, the switch will disable the port to prevent potential issues, such as insufficient power being provided to other devices that may require it. Relevance to CCNA 200-301. This topic falls under the Network Access section of the CCNA 200-301 curriculum, which covers various aspects of network connectivity, including technologies like Power over Ethernet. Understanding how PoE works, including power management and classification, is crucial for network engineers, as it directly affects how devices like IP phones, security cameras, and access points are powered within a network infrastructure. This knowledge is essential for ensuring efficient network operation and troubleshooting PoE-related issues. Brief description. When a switch port is configured for PoE Power Classification Override, it actively monitors the power usage of connected devices. If the switch determines that a device is using less power than the minimum configured threshold, it assumes the device has failed and will disconnect it. This feature helps maintain power efficiency and ensures that sufficient power is available for other devices within the network, which is critical in environments using PO technology.
Hello all. The correct answer to the question about what occurs to frames during the process of frame flooding is C. Frames are sent to every port on the switch in the same VLAN except from the originating port. Let's explain frame flooding further. Frame flooding occurs in a network switch when a frame is sent out to all ports in a VLAN except the port that received the frame. This occurs when the switch does not have a specific MAC address entry for the destination device in its MAC address table. By flooding the frame, the switch ensures that the frame reaches its intended destination, even if it does not yet know the exact port to which the destination device is connected. Understanding frame flooding is an important aspect of the network access section of the CCNA 200-301 curriculum. This topic covers how switches operate at Layer 2 of the OC model, including the learning process, MAC address table management, and VLAN functionality. Frame flooding is a critical operational concept that helps students grasp how switches manage traffic within VLANs and how they learn the locations of devices on the network. During frame flooding, a switch sends frames to all ports within the same VLAN, except for the port from which the frame originated. This action occurs when the switch does not have a MAC address entry for the destination device in its MAC address table. Flooding ensures the frame can reach its intended recipient while allowing the switch to learn the device's location for future reference. This process is essential for maintaining efficient communication in Layer 2 networks, particularly in environments using VLANs.
Hello all. The correct answer to the question regarding the function of the range of private IPv4 addresses is A. Allows multiple companies to use the same addresses without conflicts. Explanation of private IPv4 addresses. Private IPv4 addresses are designated for use within private networks and are not routable on the public Internet. The ranges of private IP addresses, defined in RFC 1918, allow organizations to use the same address space without conflict. Since these addresses are not unique globally, multiple companies can use the same private IP ranges internally without interfering with one another. This enables efficient use of address space and simplifies network management within private environments. Relevance to CCNA 200-301. This topic is covered under IP addressing within the CCNA 200-301 curriculum. Understanding the concept of private and public IP addressing is crucial for network design and implementation. The course emphasizes the importance of private IPv4 addressing in providing secure internal communications while allowing for the flexibility of using NAT, network address translation, when accessing external networks. The range of private IPv4 addresses allows multiple organizations to use the same IP addresses within their internal networks without conflicting with each other. This is essential for maintaining efficient network operations and management, since private addresses are designed for use within local networks and do not require unique global addressing. This addressing scheme supports the growth of networks and facilitates the use of NAT for Internet connectivity, allowing private networks to communicate externally while preserving internal address confidentiality.
Hello all! The correct answer to the question regarding the action that must be taken to assign a global unicast IPv6 address on an interface derived from the MAC address of that interface is C. Enable SLAAC on an interface. Let's explain SLAAC. Stateless address auto-configuration is a method used in IPv6 networks that allows devices to automatically configure their own IP addresses. When SLAAC is enabled on an interface, the device can generate a global unicast IPv6 address using its MAC address through the EUI64 format. This process allows the device to create a unique IPv6 address without needing a DHCP server. The address is created by combining the network prefix with a modified version of the MAC address. Relevance to CCNA 200 to 301. This topic is covered in the IPv6 addressing and basic connectivity section of the CCNA 200 to 301 curriculum, which focuses on the principles of IPv6 addressing, including types of addresses, address allocation methods, and the differences between IPv4 and IPv6. Understanding SLAAC is crucial for network engineers as they design and manage modern networks that increasingly rely on IPv6 due to the exhaustion of IPv4 addresses. To assign a global unicast IPv6 address derived from the MAC address of an interface, the action needed is to enable SLAAC stateless address auto-configuration on that interface. By doing so, the device can automatically generate its own IPv6 address using the EUI64 format, which combines the network prefix with a modified version of its MAC address. This method allows for easy address configuration without the need for a DHCP server, streamlining the process of connecting devices to an IPv6 network.
Hello all. The correct answer to the question about how TCP and UDP differ in the way they provide reliability for the delivery of packets is B. TCP provides flow control to avoid overwhelming a receiver by sending too many packets at once. UDP sends packets to the receiver in a continuous stream without checking. Let's explain further. B. TCP provides flow control to avoid overwhelming a receiver by sending too many packets at once. UDP sends packets to the receiver in a continuous stream without checking. This statement accurately describes the fundamental differences between TCP, Transmission Control Protocol, and UDP, User Datagram Protocol. TCP is a connection-oriented protocol that establishes a reliable connection, ensuring that packets are delivered in order and without errors. It includes features such as flow control, which prevents the sender from overwhelming the receiver with too much data at once. On the other hand, UDP is connectionless and does not guarantee delivery, order, or error checking, making it faster but less reliable. This topic is integral to the IP services section of the CCNA 200 to 301 curriculum, where students learn about different transport layer protocols, their characteristics, and their use cases. Understanding the differences between TCP and UDP is crucial for network engineers when designing and troubleshooting network applications, as it helps determine which protocol to use based on the reliability and performance requirements of specific applications. TCP and UDP differ significantly in how they handle the reliability of packet delivery. TCP is a connection-oriented protocol that ensures reliable data transmission through error checking, acknowledgement, and flow control, preventing sender overload on receivers. In contrast, UDP is a connectionless protocol that sends packets without guaranteeing delivery, order, or error checking, allowing for faster transmission but with the risk of data loss or disorder. This fundamental difference influences their respective use cases in network applications, with TCP suitable for applications requiring reliability, e.g., web browsing, file transfers, and UDP ideal for time-sensitive applications, e.g., video streaming, online gaming, where speed is prioritized over reliability. Hello all. The two differences between optical fiber cabling and copper cabling are: B. The glass core component is encased in a cladding. D. Light is transmitted through the core of the fiber. Let's explain further. B. The glass core component is encased in a cladding. Optical fiber consists of a central glass core that carries light signals, which is surrounded by a layer called cladding. The cladding has a lower refractive index than the core, which allows for the total internal reflection of light, enabling the signal to travel long distances without significant loss. D. Light is transmitted through the core of the fiber. In optical fiber cabling, data is transmitted as light signals through the core. This method of transmission allows for higher bandwidth and faster data rates compared to copper cabling, which transmits data as electrical signals. These concepts are covered in the Network Fundamentals section of the CCNA 200 to 301 curriculum, where students learn about different types of network cabling, including the characteristics and uses of fiber optic and copper cabling. Understanding the physical layer of networking, including the differences in cabling technologies, is crucial for designing and implementing efficient local area networks, LANs. Optical fiber cabling differs from copper cabling in several key ways. First, optical fiber consists of a glass core that is encased in cladding, which enables the transmission of light signals through total internal reflection. Second, data in optical fiber is transmitted as light, allowing for higher bandwidth and faster data rates compared to copper cabling, which transmits data as electrical signals. These differences make fiber optic cables particularly advantageous for high-speed and long-distance networking applications.
Hello everyone. The correct answer to the question about how CAPWAP, control and provisioning of wireless access points, communicates between an access point in local mode and a wireless LAN controller, WLC, is D. The access point has the ability to link to any switch in the network, assuming connectivity to the WLC. Let's explain further. D. The access point has the ability to link to any switch in the network, assuming connectivity to the WLC. This statement accurately describes the flexibility of CAPWAP. In a typical deployment, an access point, AP, can connect to any switch within the network as long as it has the necessary connectivity to the WLC. CAPWAP allows the AP to communicate with the WLC over the network, facilitating configuration, management, and control of the APs without needing a direct, dedicated connection between the AP and WLC. Relevance to CCNA 200-301. This concept is covered in the Wireless Fundamentals section of the CCNA 200-301 curriculum. Understanding how CAPWAP operates is crucial for network engineers managing wireless networks, as it highlights the importance of centralized management and the ability of access points to function within a broader network infrastructure. Knowledge of CAPWAP and its communication methods with WLCs is essential for effective wireless network design and troubleshooting. CAPWAP, control and provisioning of wireless access points, enables communication between access points in local mode and a wireless LAN controller, WLC, by allowing the AP to connect to any switch in the network, provided it has connectivity to the WLC. This flexibility simplifies network architecture and management, enabling centralized control of multiple access points from a single WLC. CAPWAP facilitates the configuration and management of access points, ensuring efficient operation and performance in wireless networks.
Kalimera. Hello, everyone. The correct answer to the question about which IPv6 address block forwards packets to a multicast address rather than a unicast address is DFF00:R12. Let's explain it further. This address block is designated for multicast traffic in IPv6. Multicast addresses are used to send packets to a group of devices rather than to a single device, unicast. The FF00:R12 prefix indicates that any address starting with the FFE is a multicast address, enabling efficient delivery of data to multiple recipients simultaneously. Why the other options are incorrect. A2000:R3. This address block is for global unicast addresses, which are routable on the Internet. BFC00:A7. This address block is reserved for unique local addresses, ULARs, which are similar to private addresses in IPv4 and are not meant for multicast. CFE80:R10. This address block is for link local addresses, which are used for communication within a single network segment and are not routable beyond that segment. This topic is part of the IPv6 addressing and basic connectivity section in the CCNA 200-301 curriculum. Understanding the different types of IPv6 addresses, including unicast, multicast, and link local addresses, is essential for network engineers to design and manage modern networks effectively. Knowledge of multicast addressing is particularly important for applications such as video conferencing, streaming, and other scenarios where data needs to be sent to multiple recipients simultaneously. In IPv6, the address block FF00:R12 is designated for multicast addresses, allowing packets to be forwarded to multiple devices in a group rather than a single destination. This capability enhances the efficiency of network communications, especially for applications that require simultaneous data delivery to multiple users. Understanding IPv6 address types, including multicast, is critical for network professionals in designing robust and scalable networks. Kalimera. Hello, everyone. The correct answer is B. TCP provides flow control to avoid overwhelming a receiver by sending too many packets at once. UDP sends packets to the receiver in a continuous stream without checking. Let's explain further. TCP, Transmission Control Protocol, is a connection-oriented protocol that provides reliable delivery of data. It uses flow control mechanisms to ensure that the sender does not overwhelm the receiver by sending too many packets too quickly. TCP establishes a connection through a three-way handshake, sequences packets, acknowledges received data, and retransmits lost packets. UDP, User Datagram Protocol, on the other hand, is a connectionless protocol that sends packets called datagrams without establishing a connection. It does not provide flow control, error checking, or acknowledgement of received packets, which means it sends packets in a continuous stream without checking if they are received successfully. This makes UDP faster but less reliable than TCP. Relevant topic from CCNA 200 to 301 is Network Fundamentals. TCP IP Overview. What is the difference between TCP and UDP? Kalimera. Hello, everyone. The correct answers. B. The glass core component is encased in a cladding. D. Light is transmitted through the core of the fiber. Let's explain further. Optical fiber cabling and copper cabling have several key differences. Option B. The glass core component is encased in a cladding. In optical fiber cables, the core is made of glass or plastic and is surrounded by a cladding layer. The cladding has a lower refractive index than the core, which keeps the light signals confined within the core through total internal reflection. This design allows the light to travel long distances with minimal signal loss. Option D. Light is transmitted through the core of the fiber. Optical fibers transmit data as pulses of light emitted by lasers or LEDs. The light travels through the core of the fiber optic cable, allowing for high-speed data transmission over long distances without the electromagnetic interference that affects copper cabling. Why the other options are incorrect. Option A. A BNC connector is used for fiber connections. Incorrect. BNC, Bennett-Neal-Conselman, connectors are typically used with coaxial copper cables, not with fiber optics. Fiber optic cables use connectors such as SC, ST, LC, and FC. Option C. The data can pass through the cladding. Incorrect. The cladding in a fiber optic cable does not allow light, data, to pass through it. Instead, it reflects the light into the core, ensuring the signal remains strong over long distances. Option E. Fiber connects to physical interfaces using RJ45 connections. Incorrect. RJ45 connectors are used with twisted pair copper cabling, such as Ethernet cables. Fiber optic cables require specialized connectors, e.g., SC, ST, LC, and interfaces designed for optical transmission. Kalimera. Hello, everyone. Correct answers. A. 5 GHz provides increased network capacity with up to 23 non-overlapping channels. C. Cells that overlap one another are configured to use non-overlapping channels. Option A. 5 GHz provides increased network capacity with up to 23 non-overlapping channels. The 5 GHz frequency band offers significantly more non-overlapping channels compared to the 2.4 GHz band. Specifically, it provides up to 23 non-overlapping channels, depending on regional regulations, which increases network capacity and reduces interference. This allows for better performance and more access points to operate simultaneously without causing co-channel interference. Option C. Cells that overlap one another are configured to use non-overlapping channels. In wireless network design, especially in environments requiring multiple access points for coverage, it's standard practice to configure overlapping cells on non-overlapping channels. This minimizes interference between access points and ensures a stable and efficient network. Assigning non-overlapping channels to adjacent access points that have overlapping coverage areas prevents signal overlap from causing degradation in network performance. Why the other options are incorrect. Option B. 5 GHz channel selection requires an autonomous access point. Incorrect. Channel selection in the 5 GHz band does not require autonomous, standalone access points. Modern wireless networks often use controller-based architectures where the wireless LAN controller, WLC, manages channel selection dynamically across all connected access points. Option D. Adjacent cells with overlapping channels use a repeater access point. Incorrect. Using repeaters in overlapping cells with the same channels is not a recommended design, as it can increase interference and reduce network performance. Instead, overlapping cells should use non-overlapping channels to mitigate interference. Option E. For maximum throughput, the WLC is configured to dynamically set adjacent access points to the same channel. Incorrect. Configuring adjacent access points to operate on the same channel can lead to co-channel interference, which degrades network performance. For maximum throughput, adjacent access points should be set to different non-overlapping channels.